Binomial radical expressions is the name of the topic we're working on right now. Just to clarify some meanings, like radicals, if you hear that phrase, it just means that we are working with radical expressions that have the same blank and blank. What are those two words going to be? The first word is going to be the same index. The index is the number in the little hook of the radical. So for example, that is a square root, fourth root, cube root. Same index, and they also will have the same radicand. The radicand is the expression underneath the radical sign. So those are going to be like radicals. And when we are dealing with binomial radical expressions, those are separated by plus or minus signs. So to warm up, a couple things to point out. If you had something like 5x plus 3x, well, adding that has become second nature to you. That is just going to be equal to 8x. If you think about it, you're really factoring out the x, you're factoring it out, and you're left with 5 plus 3 on the inside. 5 plus 3 is 8, so you're left with 8x. Here, again, addition, 5x squared plus 3x squared. If you factor out x squared, undistribute that, okay? You're left with 5 plus 3 again. That's why it's 8x squared. But we do these and we don't think about what's really going on behind the scenes, and that's what helps, that's what causes us to get stuck on trickier examples. So if I gave an example like this right off the bat, there would probably be a lot of issue, and some of you are probably already thinking of doing some wrong stuff. Okay, so think in your head, what do you want to do for this example? And now I would tell you we need to factor out a 2 to the x power. That leaves us with 5 plus 3 on the inside. 5 plus 3 is actually equal to 8. So you have this 2 to the x and you have times 8. So I could either leave it like this or maybe out front. I have 8 2 to the x's. You can be done right now. Now, is there a little bit of a bonus that we can put with this? Yes. Here's our little bonus. If this confuses you, don't stress, but what I wanted you to see is you're just combining how many 2 to the x's we have. PEMDAS, order of operations, you cannot multiply that to 16 to the x power. Oh, that got a little messy. You cannot multiply that to 16 to the x power. It just stays as it is. When we deal in another chapter unit with exponentials and logarithms, I'm just cleaning this up. Exponentials and logarithms, you're going to, and I've been stressing this for months now, you're going to rewrite things with its lowest prime base as possible. It won't always be prime, but if you can, you definitely want to go for it. 8 is really equal to 2 to the third power. 2 to the x is 2 to the x. Well, now you're multiplying like bases, so what do you do with the exponents? If that was x to the third and x to the second, you would get x to the what? Fifth. And the way you would get that is you add your exponents. This is from properties of exponents. The same rule applies, right? Same rule applies. You have the same base that doesn't change, and you add the exponents. So you could write 3 plus x or x plus 3. So really, there's many ways that we could write this same expression over here. So again, that was 2 to the x times 8. So these are all equal, but for what we're doing right now, we're really just combining how many of the same thing we have. 5 square root of 2 plus 3 square root of 2. Well, this is what we're prepping for. We have like radicals. They're both square roots and they're both 2's inside. Yes, you can add and subtract. That gives us 8 square root of 2. If you had to show work, you're really showing the distributive property by reverse distributing or factoring, and you're left with the 5 plus 3 inside, and that's where this solution comes from. So I keep using the same numbers because I really just want to highlight what is happening in each of these cases. Again, like radicals, you have the same index, same radicand. We'll get 13 square root, or fourth root rather, really tucking it in there, x, y. Done. That is the solution. What is the name of the radicand in the quadratic formula? Anyone remember? Think about it. I'll tell you the answer after the next example. Here, these look like they're not like radicals. We have a cube root on both of them, but we don't have the same radicand. However, can you simplify this at all? Can you take the cube root of 125, or a number that creates 125? Yes, a factor of it. 125 is a perfect cube, and the cube root of 125 is 5. Same over here with the 27. What is the cube root of 27? It's 3. So my next step is going to be 5 times the cube root of. Now what's going to be left inside? X squared, y, z minus. I'm going to take out a 3 because the cube root of 27 is 3. Really make sure the index is in the index. And again, I'm left with an x squared, y, z inside. Cross your z's. They look like 2's. Well, if I factor out this big cube root, I'm left with the 5 minus 3, and 5 minus 3 is 2. So really, I have for an answer 3 times the cube root of x squared, y, z. There we go. Now our question from before, what was the name of the radicand in the quadratic formula? That's called the discriminant. It's a specific name for that radicand. So that one has a special name. All right, next thing. We're going to be adding and subtracting right now. Let's just kind of cover up a few examples so we don't get too far ahead. When you're adding and subtracting, if we want to write a rule for this now, what is essentially the rule going to be? You factor out your greatest common factor. You're going to factor out the nth root of x, and what is left inside? You're left with the a plus, or minus some b value. It doesn't mean both, it means or really. Or you can even write it commutative property. You could turn it around, so you could write this out front. A, add or subtract the b value, whatever the operation indicates for you to do, and then you have the nth root of x next to it, one way or another. So essentially you're just adding this coefficient, or whatever's out front there. Okay? So here's our rule, and now we're just going to apply it. So what's our answer here? 1 square root of 5x, and there's nothing left to simplify. We're good. Next. Cannot be simplified. They are not like radicals. Next. Look pretty good. However, my index is 3 and 5. Nothing I could do about it. Cannot be simplified. Next. They're both 5s. Index different. Nothing I can do. Cannot be simplified. So you'd be surprised how many things cannot be simplified. Don't try to get creative and force it to work. That's when you invent new math, okay? Do not invent anything. Now I have 3x square root of xy plus 4x square root of xy. Can you factor out the square root of xy? Sure. You could actually even factor out the x and square root of xy. What does that leave you with? The 3 plus 4. Do you have to show this step? No, not at all. That's 7. So final answer, could you just jump to this? Yes. If you can jump right to it, by all means, go ahead. And that's your answer. All right, a few more. Over here, 17 fifth root of 3x squared. Yep, we're good. So it's 2 fifth root of 3x squared. Can I take the fifth root of anything in there? Nope. So we're done. Next, they don't look like radicals, but 12, what makes 12? 12 is really 4 times 2, and 4 is really 2 times 2. So we have 2, 2, and 3. That's 12. 75. It's 25 and 3, so it's 5, 5, and 3, minus square root of 3. What else can I do? Perfect square is 4, 2 comes out, so I have 2 square root of 3. 25 is a perfect square. Got a pair of 5s. Take that out. 5 square root of 3 minus, really, that's a 1 square root of 3. 2 square roots of 3's plus 5 square root of 3 is 7. Take away 1 is 6 square root of 3. Done. Next. Maybe the same thing here, right? 250. It's even. I always start with the even fact. So that's 125 times 2. I'm not going to break down 125 this time. I'm going to change up how I'm writing it. It's 125 times 2 plus cube root of. You saw this number the other day. That's also 27 times 2. I'm not going to break down the 27. Minus, yeah, I know you might be good and know that it's 2 times 2 times 2 times 2, but I'm going to try to follow the same procedure. I'm going to do 8 times 2. Now, each of these numbers happens to be a perfect cube. You got to plan ahead so that you make good decisions, okay? So I went down first. I'm going to go over because I don't have that much room. 125, the cube root is 5. So I have 5 cube root of 2 plus 3 cube root of 2 minus 2 cube root of 2. I could factor out a cube root of 2. I'd be left with 5 plus 3 is 8 minus 2 is 6. Final answer, 6 cube root of 2. So that's it. I'm just going to take this green because I didn't know where to draw my line here, and we're good. Okay, next rule or practice. What do I got here? I have another rule. Now multiplying. We've been over this and we've been practicing it, so it shouldn't be too much. But I have a nth root of x times b nth root of y. The rule's a little bit more lax, okay? When you're multiplying, similar to fractions. With fractions, you need a common denominator. It's a little bit more strict when you add or subtract. But when you multiply, you don't need a common denominator. When we add, we need like radicals. They need the same index, same radicand. But when we multiply, we don't. We don't need the same radicand. We just need the same index for right now. So what will happen? You're going to multiply the a and the b. So I'll show that like this. That means I'm going to multiply those numbers out front. And then I'll have the nth root, the common radical, that's the same for both of them, same index. And I will multiply my radicands together. Make sure, some of you when you were writing things out, you are forgetting to make sure that the top of your radical covers everything you're taking the root of. So be really extra about all of that. All right? So in a nutshell, that's what we need to do when we're multiplying. Now, what do we have here? I'm multiplying binomials. So I'm going to put a little note. So when you see maybe a header that says multiplying binomials, if you write this phrase out, it might stick in your head a little bit better and be like, oh, we definitely did that. So we're multiplying binomials. You might think to yourself, FOIL. Sure, you could call it FOIL. You could call it distribution. I'm going to distribute the 3 to each of these. I'm going to distribute radical 7 to each of these. I'm going to multiply these all out using different language each time so you could see it in a new way each time. 3 times 5 is 15 plus 3 times the square root of 7. 3 is on the outside, square root of nothing. Square root of 7, well, not nothing, but square root of 1 really. And then 7 under that radical has a 1 as a coefficient. You get 3 square root 7. That is the product. That's first and outer, if you will. Now negative square root 7 times positive 5 is minus 5 square root of 7. And then, so I distributed that. Now I'm distributing it here. Positive, negative is negative. Square root of 7 is 7. If you need to write square root of 49 first, sure, knock yourself out. But like, you're going to have big numbers sometimes. So if you could just please remember, when you multiply a square root of something by the square root of the same thing, as long as that thing is positive, you're going to get that number on the inside back. So it's 7. Now we just clean up a little, combine like terms. 15 minus 7 is 8. 3 rad 7 minus 5 rad 7. We're going to use what we used on the last page of notes. You get negative 2 square root of 7. And we're good. Done. That is it. Nothing else to do, nothing else to simplify. Next. Another way to think of this is you can kind of think of distributing this whole binomial. So that's why I said I'm going to switch it up. This whole binomial can get distributed to that and then to that. How is that different from what I just did? Well, in the last example, what we did was we multiplied the 3 by the 5, then the 3 by the square root of 7. Then we multiplied negative square root of 7 by 5 and negative square root of 7 times positive square root of 7. So I just took turns with each thing. This time I'm going to think of this whole yellow thing multiplying and distributing to that, and then it all multiplying and distributing to that. Well, what happens? We get this times that. The 2 is there, and it's being multiplied by that whole entire 3 plus 2 square root of 5. And then, that's done, plus sign. This is multiplying by all of this. So 4 square root 5 is being multiplied by 3 plus 2 square root of 5. Well, now what? Well, now I'm going to do my little baby distribution. Do that, and do that, what happens? 6 plus 4 square root of 5 plus 12 square root of 5 plus, what's this going to be? Can you do it in your head? Giving you a chance. Think you got it? What's 4 times 2? What's square root 5 times square root 5? Clean it up. What'd you get? If you got 8 times 5 is 40, you're good. Okay? Then if we combine like terms, you're going to get 16 rad 5, and you're going to get 46. So 46 plus 16 rad 5. Done. Okay? Same exact idea. If you did them, this technique on the first one and this technique on that one, I promise you'll get the same answer. Here, notice anything about these two things? Any special words stand out? Anything you want to discuss? If you said conjugates, you're a genius, okay? Make sure you know your vocabulary. Conjugates are awesome. Why are conjugates awesome? Because your outer and inner parts of your multiplication are going to cancel out. They're going to be the same expression, but one positive, one negative. If something's positive and the other's negative, what are they of each other? Opposites. But is this expression the opposite of this expression? No. The opposite of this would be a negative 5 and a positive rad 7. Just the sign in the middle changing, that means conjugates. Use the right words, okay? So when you distribute first times first, you're going to get 25. I promise, outer and inner will cancel. You're going to have a positive 5 rad 7 and a negative 5 rad 7. It is gone. Minus square root of 7 times square root of 7. Keep track which ones have square roots and which ones don't. So it's just going to end up being minus 7. If you need to press pause and figure out why it's 7, please do so. That gives us, final answer, 18. So what's cool about multiplying conjugates with radicals? Your answer won't have radicals. Where did we do something like this before? Where did we multiply conjugates and get rid of some secret radicals? I'll tell you after the next example. Maybe think about that. Here's another set of conjugates. Maybe you're quicker at it this time. 36 minus 12, 24. If you said when we were doing imaginary numbers and we had something like 2 plus I in our denominator, we multiplied by 2 minus I, then you're right, because I is the square root of negative 1, so we had a radical in our denominator. You have to rationalize your denominator. A radical is an irrational number, and when you rationalize something, you change it from being irrational to being rational. When you rationalize with an irrational person, you are trying to make them less irrational or not irrational at all, hopefully, ideally. All right, here again are conjugates, some quick multiplication. You should get 9 minus 8. Your final answer is 1. So then why do you think this is going to be helpful? Based on what we just talked about a second ago. I'll tell you after the next example, but maybe think about that. 4 times 5. They're not conjugates, so I can't just do a shortcut, okay? 4 times 5 is 20. 16 rad 2. 10 rad 2. 16. If you don't know why that's 16, please press pause and figure it out, okay? And then come back. 26 rad 2 and 36. That is finished. So that's the end of this page. So why do you think that's going to be useful? Why are these conjugates going to be useful? For dividing and rationalizing denominators. Okay. Last lesson we dealt with just having a monomial, I guess, like a single expression in your denominator. And through, you would need n number of things, of each expression, of each factor. You would need n number of them, or a multiple of n, in order to simplify. So need some multiple of n, the least possible, please, of each factor of the radicand. You might want to check that last video if you're not sure what I'm talking about, but it was the last two examples in the last video, okay? So you're going to need some multiple of n of each factor of the radicand in order to rationalize. But when you have a binomial, a sum or a difference, what are you going to need? Our good friend, the conjugate. Okay? That's a little sloppy, sorry. So here's our first example. What are we going to multiply on top and bottom by? Let's just get right to it. This is Algebra 1 review. Rad 5 plus rad 2, whatever you multiply by on bottom, we multiply by on top. Top we're going to distribute. I'm going to get 3 square root of 10 plus 6. If you are struggling with this, you need to hit pause and figure it out, okay? 5 minus 2. So 3 square root 10 plus 6 over 3. Pretzel reduce. I get square root of 10 plus 2. Okay? Next example. Here's our next example. Maybe you get a head start while I sketch in the pretzel I'm talking about for people. So I had a minus sign there. I changed it to a plus sign since they're all minus examples. Conjugate. Rad 3 plus rad 5. Rad 3 plus rad 5. Both places. Distribute. You get 2 square root of 21 plus 2 square root of 35. Neither of those numbers simplify. 5, 7, 3, they're all prime. Nothing will break down. Here, 3, oops, 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 oops. I totally lied. These should be minus signs. Please, please, please make them minus signs. That's a minus sign. 3 minus 5, which is negative 2. Pretzel out the negative 2. What do I get? Negative square root 21 plus square root of 35 again. Any issues? Press pause and come back. Last example for right now. If this top is a binomial though, you would just FOIL out on top 2. This time we don't have 2 radicals, we just have 1, so it's 3 plus square root of 6, the opposite sign of the middle. 3 plus square root of 6. Sorry, here, and I wanted to change it to make it different and I messed up writing it, so forgive me. Distributing, we have 12x plus 4x square root 6 all over 9 minus 6. Can I do anything? Let's see, 9 minus 6 is 3. I could reduce a little, so you could write this answer 2 ways. You could write 12x plus 4x square root 6 all over 3, or if it's multiple choice and you need a way to check, or if your friend wrote the answer differently than you, so this is totally acceptable, this check mark, great. Reduce each one. That would become a 4x, but each part would have to divide by 3. You can't just divide part of it by 3. Plus, I could leave that as 4x over 3 square root 6. Both of these answers are acceptable. All right? So in a nutshell, that is what we are working on in this section. Hope you got it.